I am retired since nearly 2 years now.
Okay, so the teaching burden is not.
Yeah,
there.
so I continue doing research, but no teaching.
Now?
No.
Prashanjit?
Yes.
Can you make me co-host here? Because I think in this account it is not co-host.
I'll make it. 1 second. I'll just put the YouTube live and I'll make it. Okay, so you're co-host now.
Okay, just going to check. Yes, the option is open. Okay, fine.
So just on a different note, just on a different note,
Yeah.
Just wanted to say that now this French Open is going on. Do you follow tennis?
What? The?
French Open? Tennis?
Oh, yeah. I'm not fan of tennis.
Okay.
Yeah, I know. Maybe I can switch on the live. It can be better.
So we can start now?
Yes, we can start.
Okay. So on behalf of the organizers, a very warm welcome to Professor Jean-Pierre Raymond and all the participants of the webinar on PDE and related areas. For the participants, we request you to keep your questions stored in the question answer box. We are honored to have Professor Jean-Pierre Raymond with us today. Professor Raymond obtained a doctorate at the Paul Sabatier University, Toulouse, France in 1982. From January 2009 up to January 2011, he was deputy chairman of the Mathematics Institute of Toulouse, Institut des Mathématiques de Toulouse, IMT. He was one of the first professors of the French-Indian Cyber University in Science, FICAS, in 2003, a joint program between France and India from 2003 up to 2010. From 2012 up to February 2018, he was the Deputy Director of the Indo-French Center for Applied Mathematics, IFCAM, a joint research unit in applied mathematics between France and India. He is the professor at Université Paul Sabatier Toulouse III, Institut des Mathématiques de Toulouse, France, since 1991. His research areas are partial differential equations, numerical analysis, control theory. In fact, control of fluid flows, very specific to Navier-Stokes equations, boundary layer models, optimal control, analysis and control of fluid structure models, numerical approximation of optimal controls, and of stabilizing controls. He has been awarded the SIAM Activity Group in Control and System Theory Best SciCon Paper Prize in 2011. I suggest students and young researchers to look at his lecture notes, slides and papers on control of partial differential equation, which has been remarkable quality of being accessible to the very beginners, yet maintaining their advanced standard throughout. Today, he will be speaking on existence and uniqueness of maximal strong solution of 1D blood flow in a network of vessels. I hope you will enjoy the talk thoroughly. Professor Jean-Pierre Raymond, it's over to you now.
Thank you very much. So thanks for the introduction, but also thanks for inviting me to this nice seminar on PDE, webinar on PDE organized by IIT Kanpur, TIFRK, ISER Pune, and ISER Calcutta. It's a great pleasure to be in India, at least virtually. So I'm going to speak of a project. Yeah, sorry, something appeared in the screen. So on a project funded by the research agency in France, and we started working on that with Debayan Maiti and Arnab Roy, two colleagues from India, before the beginning of the project. So the project is about human and animal numerical models for the craniospinal system. So the first question is, why studying mathematical model of blood flow in the brain? So the goal is to use a generic blood flow model and to use flow rate measurement or some other type of measurement in order to adapt this generic model to a specific patient, to estimate some physiological parameter like property of a vessel, to estimate the blood flow pressure in the brain, which is not accessible by probe, contrarily to what happened for the cardiovascular system. So the knowledge of pressure and of some parameter may be very useful for studying aging, and it can be an help for diagnosis in some disease. So this is the aim of the project, and today we are going to speak and to present some generic model of blood flow. So what is a blood flow model in the brain? So for that, we have to first to describe the network of vessel. So the geometrical property of a vessel, the arterial system, the venous system, and in between the microcirculation corresponding to exchange of oxygen. We have to specify some parameter, and in order to describe the velocity and the pressure in the vessel and also the vessel deformation, we need some equations, some boundary condition, and we also need to know the external pressure exerted by the brain or the cerebrospinal flow in the brain. So for that, we have to make a coupling between this system of equation and another one for the cerebrospinal flow in the brain and also in the spine. We can also study some other phenomenon like the autoregulation, which is a biochemical process, a kind of feedback mechanism in order to maintain the blood flow in a good regime, nearly constant flow rate when there are changes. But today, I'm going to present only model for blood flow. So we consider that this is known, this is also known. So the question is how to find this geometry. So this geometry can be found thanks to medical imaging. So for example, with magnetic resonance imaging, we can have this kind of picture. Actually, we have a 3D description of the brain. So we can see arteries, veins. So in these two pictures, we can see the network, the representation of the network of the cell. Since we have a 3D representation here, we can make some cut. So if we take the cutting plane B or C, we observe this. So this corresponds to the cut of some vein here or some arteries. And the same here for the cut C. But we can have nearly real-time evolution of these images. And thanks to that, we can recover the flow rate in some arteries or some vein, and this can be used for estimation, for the estimation process. Okay, so what is used actually in to describe blood flow, not only in the brain, but also in the body. In that case, we speak of the cardiovascular system. It corresponds to a model for the heart, arteries, and veins in the body. So at the 3D level, there are some models, at least partial model for the cardiovascular system. It consists in coupling the Navier-Stokes equation with the evolution of the vessel modeled by membrane or shell equation. But we do not have such a description for blood flow in the brain. Why? Because there are a lot of different types of scale, and it seems very difficult to have such a model for the brain. Even numerical simulation, if such a model existed, are beyond the capability of current computer. And so we have to do something else. So we have to look at a simpler model, like one-dimensional model, which are nowadays used quite a lot for the cardiovascular system, but also for the blood flow in the brain. So in this model, we have a network of branches. So each vessel is represented by a branch, and the blood flow velocity is described only by one dimensional spatial variable. And the deformation of vessel is described through the variation of the cross-sectional area of a vessel. So this more or less corresponds to the 1D model, and this is the main, describing this type of model is the main goal of this talk. There are also some simple model. 0D model means only OD model, in which we take the same geometry as before, but in the branches, we assume that there is no variation of the pressure and the flow rate with respect to the spatial variable. So we obtain a system of OD. Okay, so what is known for this type of model? So for the 3D model, fluid structure interaction model in a complex geometry like a network of vessels, there is no existence result up to now. There are some existence results, but only in a very simple geometry, like in a cylindrical tube, 3D model. These results are due to Muir and Kanik in 2013 and 15. I will give some details about that. And recently with Debayan and Arnab, We have also obtained the existence of maximal strong solution for this type of model. But this is only for a very simple model corresponding to a tube. Sorry, so we have also, okay, for 1D model, there are existence results, but also in the case of a single vessel or a single vessel coupled with a kind of boundary condition called Vinkesel boundary condition. And in that case, because the vessel is assumed to be elastic, we have a quasi-linear hyperbolic system, which is strictly hyperbolic and in a subcritical regime. These results are due to Kanik and Kim in 2002, and some paper by Quarteroni and co-author in 2005 and also earlier. Up to now, there is no existence result for a network of vessels, even a simple network like bifurcation as I presented before. And this is what I'm going to present today. But we assume here that the vessel is viscoelastic. We also obtain energy estimate. So this is the result obtained with Debayan and Arnab. But I would like to say that the viscoelastic behavior of vessel seems to be natural. It has been observed in many experimental studies, and it gives better prediction than those obtained with elastic laws. So even if it seems to be a simplification, it seems to be also better for the modeling of blood flow in the brain. Okay, so the plan of the talk is the following one. In the first part, I will present the model. The analysis is done in the second part and some extension in the third one. So let us look at a simple model like that, like a bifurcation. As I said before, there is no existence result for that. And so what is done up to now? What are the known existence results? It's only for the 0D model. So a system of OD. So in the system of OD, the domain is split into different portions like that. And in each part, the pressure and the flow rate are modeled by a system of OD, and this is based on some analogy with electric circuit. I will present this analogy later on. And so what we can do, we can try to find something just for one piece like that. So in a cylinder, what I'm going to explain is what is known in a cylinder and how we can derive the 1D model for a cylinder and next for a network. So in this cylinder, R here, capital R, is the radius of the cylinder. And L is the length of the cylinder. So we assume that R is small with respect to L. So omega describes this reference configuration. It corresponds to point for which the radius is less than R. X varies between 0 and L. Gamma S corresponds to this part of the boundary. It corresponds to the vessel. And omega is used to describe either gamma S or some of the quantity. So it corresponds to X and theta. So in the model I'm going to present, we assume that eta, which is the displacement from the reference configuration, the displacement of the vessel, we assume that the displacement is only in the radial direction. So this vector here is equal to this function, which is a scalar function, times the normal, here denoted by NR, the normal to the boundary gamma S in the, it's supported by the radius. So the deformed configuration here is represented because due to the boundary condition that we have, the fluid flow deforms the vessel. So we may have either a kind of Neumann boundary condition or Dirichlet. So this is what is called the inflow boundary condition, and this is the outflow. And the deformed configuration for the deformation, the displacement eta is given here. And the deformed boundary is denoted by gamma eta t. So what is known in this case, we know some existence result when the fluid is described by the classical Navier-Stokes equation, and the vessel is described by a shell equation. So to describe, to give Navier-Stokes formulation, we introduce the Cauchy stress tensor here. U is the velocity, P the pressure, and mu correspond to the velocity of the viscosity of the fluid. So we write the equation in the deformed configuration. We write the conservation of mass and the conservation of momentum here. Rho corresponds to the density of the fluid, so of the blood, if it is the blood. So these are the main equation. We need some boundary conditions. So on the vessel, we write that the velocity of the fluid here is equal to the velocity of the displacement. And so it means that only the radial component of the velocity is non-zero. The longitudinal velocity is zero at the boundary, and also the angular velocity is zero. So we complete by some inflow and outflow boundary conditions, which are either Neumann boundary condition or Dirichlet, plus the initial data. So when we know this quantity, we can solve the Navier-Stokes equation, but this quantity is linked, it corresponds to the velocity of the displacement. So it's given by the equation for the displacement. Here it's a shell equation, a very simple shell equation. Laplace S here, delta S is the Laplace-Beltrami operator on gamma S. And this is the classical B Laplace operator. This is the damping term. We assume that beta 2 is positive, beta 1 is non-negative. And this term here, okay, this term, when I do not take the external pressure, correspond to the force exerted by the fluid onto the structure. J here denotes the Jacobian of the transformation induced by the deformation. Sigma is the Cauchy stress tensor, and R here is the normal to gamma S, and N tilde is the normal to the deformed configuration. Okay, what is this strange term here? So we assume that the vessel are in the brain, and so there is some external pressure due to the cerebrospinal fluid, and this term here corresponds to the external pressure. So usually it's not given here, but okay, we have to put it. We take some boundary condition at the boundary of small omega here for eta and some initial data. So these are the two equations which are coupled here by the equality of velocity and here by the equality of force. Okay, so as I explained before, there are some existence results for this simple cylindrical domain here. So when there is no viscosity, beta 1 is equal to 0, and when the boundary conditions are given on the pressure, there are existence results by Mua and Kanik in Archive for Rational Mechanical Analysis in 2013, existence of global weak solution, and another result in which they also take into account longitudinal displacement of the vessel in 2015. So very recently, with Debayan and Arnab, we have obtained the existence of maximal strong solution in the case when there is a damping here. And the paper is accepted in Siam Journal on Mathematical Analysis. So what kind of result we obtain here? We look for strong solution. So more or less nearly for you, L2 with values in H2 and H1 with values in L2. But because we take Neumann boundary condition, there is some loss of regularity here. So we have not exactly H2, but a little bit less. And the same for the pressure. In place of having L2 with values in H1, we have something weaker here. So this is the regularity for the displacement. We have to assume that R plus eta remains strictly positive. It means that there is no shrink to 0 of the vessel over the time of existence. And so we obtain the existence of a maximal strong solution, means up to a time Tm, for which either this norm may explode or this quantity also may explode. It means that at time Tm, so this norm here corresponds to the norm of U in this space for the pressure in this space and eta in this space. So either this quantity remain bounded and the solution exists, or if it is unbounded, we lose the existence of the solution, but we may lose also the existence of solution if this quantity here goes to 0. So this is the type of result we have obtained. And this is the exact statement. So we need some regularity condition on the initial data and some compatibility condition. So I do not say more on that. And so now I would like to explain how we can obtain the 1D model. So to obtain the 1D model, we assume that eta is independent of theta, the angular position. And so eta depends only on t and x. To describe the evolution, we introduce the cross-sectional area, which is the area of any section here at the point x and time t. We also assume that the angular velocity here is 0. So ux is the velocity in that direction and along the longitudinal axis, and ur is the velocity in the radial direction. And we also introduce the flow rate, which is a product of A and the mean value of the longitudinal velocity. So if we write the Navier-Stokes equation in cylindrical coordinate, we obtain these two equations since there is no equation for UD. We also have the fact that because of that, U is independent and P are independent of theta, so depends only on T, X, and R. And this is the divergence condition. So to obtain the 1D model, I present the method introduced by Kanik and co-author in many papers, where they use the method of asymptotic expansion. So the idea is to say, okay, epsilon, which is R over L, is a small parameter. And so we are going to expand the velocity and the pressure in terms of the power of epsilon times here some quantity in order to have a non-dimensional form. And we put this expansion into the equation and we keep only the power up to epsilon to the power 1. So this is called the epsilon 2 approximation of the system. So the corresponding quantity here is denoted by V, and the corresponding pressure by Q. And so in this epsilon 2 approximation, we obtain the equation for Q and V in this form. So the main conclusion here is that Q does not depend on R. And so in this approximation, we take a pressure which depends only on T and X. So we have to do the same for the shell equation. So for the shell equation, first I look only at the right-hand side here, and the epsilon 2 approximation of the right-hand side is nothing else than P minus the external pressure. Why? Because this is close to the identity in the approximation. This is close to N, and so taking just this inner product gives this quantity. Okay, and so now we can obtain the 1D model in a very simple way. So to do that, we take the average of the previous equation over a cross-section, and we obtain the first equation, which is the mass conservation equation, and the momentum conservation equation, which is an equation for Q, and this is an equation, evolution equation for A. So here rho is the blood velocity, Kf is the friction coefficient, depending on the blood viscosity. So how this is so simple? So if we start, for example, from the divergence condition, if we integrate over a cross section, so this is the exact integration because the integration with respect to theta gives 2 theta since U does not depend on theta. So we obtain exactly this and exactly this because we can show that the other terms are 0. And this is nothing but the time derivative of A. Why? Because this corresponds to the time derivative of eta due to the compatibility condition. And this is nothing else than the space derivative of Q. So we see that the divergence condition gives this, and we can do the same calculation for the mass for the conservation of momentum equation. Calculations are a little bit more complicated, but we obtain we obtain exactly that equation. Okay, so now to close the system, we have to take the epsilon 2 approximation of the left-hand side of the equation. So I write the shell model in a more complete way here. So I recall that eta depends only on x and t. So now the Laplace Beltrami operator is just the second derivative with respect to x. So the right terms here correspond to what we had previously, and I have added some other terms here. Okay, so what is interesting in this epsilon 2 approximation is to see what is small and what is large. Okay, so in this analysis, I have written here the coefficient in the equation in terms of h, which is the thickness of the shell, and r, which is the radius of the vessel. Okay, we know that r is small, but h is much smaller, and so h over r is also small. And when we look at the expression of this coefficient, we see that the two dominant terms are these two ones. And this gives the epsilon 2 approximation of the shell equation, which is written here. So if we recall that eta is linked to A by this equation, and if we introduce the cross-section of the reference configuration, we obtain this expression for eta, and finally, we obtain the expression of the pressure minus the external pressure in terms of A with two coefficients here, beta and eta. And so this is the system we finally obtain. So the complete system is this one, the first equation for AQ, the evolution equation for Q, the pressure, the law for the pressure given here, which is a viscoelastic law if nu is strictly positive, and this is the case that we consider here. And I have to mention here to recall the fact that beta and nu actually depends on the reference configuration in this way. So if we replace this quantity here, we obtain exactly the model that we are going to study. The associated hyperbolic model is for nu equal to 0, and when nu is positive, we have a coupling between an hyperbolic and a parabolic equation. So I have to go a little bit faster. So now I would like just to present the equation for the cross-section and nu, so we can make a change of unknown using this. So if we substitute Q by AU in the equation, we obtain this set of equation. And if we replace P by the pressure law, we obtain this set of equation. I do not give more details, but I need that later on. Okay. So a few words about the electrical analogy. So in the electrical analogy, we identify the difference of pressure with the difference of potential and the flow rate with the current. And the system is obtained by taking the AU system, linearize around the reference configuration and the velocity equal to 0, and write the equation in terms of P and Q. So if we do that, we obtain exactly this set of equation. We can write in this form, so I introduce some coefficient. And now we would like to have some system of equation independent of x. So we have to take the integration with respect to x over the interval 0L, and we obtain this set of ODE. So in this ODE, we see that we describe the mean value of the pressure over the segment 0L, the mean value of the flow rate, but there are two equations and 4 unknowns. So we have to in order to close the system, we have to specify what are the something at the entrance of the circuit. So we have to specify, for example, the pressure at the entrance and the flow rate at the exit. So if we do that, it remains 2 unknown quantity, and we say, okay, we identify P bar with PL and Q bar with Q naught. And this is how the 0D model is obtained. So we can introduce inflow pressure and outflow rate, and the same here. And we end up with this set of equations, which is the analog of this circuit. Okay. So now I finish this part by introducing the equation for a network. So to simplify, we take a very simple network corresponding to a bifurcation. So here we have 3 vessels. So the vessel number 1, 2, and 3. So in each vessel, we have to describe A and Q. This is why A and Q now are indexed by I. And so we write the same set of equations as before, but in each vessel. So we have an equation for vessel 1, vessel 2, and vessel 3. So for simplicity, I assume that now the interval is 0, 1, so L is equal to 1 for the 3 vessels. And so in this vessel, X varies between 0 and 1, and I take the same description here, 0, 1, in that direction. Okay, so I have a set of equations, but I have to specify what happened at the junction. And so at the junction, I write that the inflow rate for Q2 and Q3, so the sum of the 2 inflow rate correspond to the outflow rate for the vessel 1. So we write the balance of flow rate like that. And we write that the pressure at the extremity of vessel 1 is equal to the pressure at the extremity of vessel 2 and the pressure at the extremity at the origin of vessel 3. Okay, but we have to take into account what is called the static pressure, but also the pressure term corresponding to the velocity, which is called the dynamical pressure, because Q1 over A1 is just the velocity. So this is what is called the total pressure. So these are the 2 equations at the junction, and we complete the system by some boundary and some initial condition. Okay, so let us start now with part 2, where we analyze the model. So I have written here the full nonlinear system in each part of the vessel with the junction condition and the initial condition. And so what we do to study this system, we linearize the system around the initial condition. So in each part, of course, there are some additional nonlinear terms. And so using this linearization, we have to introduce some coefficients here, depending on the initial condition. So the AQ system can be described like that. So we have put here in the left-hand side all the nonlinear terms. So there is one nonlinear term in the evolution equation for Q in each branch. There are also a nonlinear quantity at the junction here, G1, G2, and G3, plus some term here, which is constant, but that we have to take into account. So this is a writing of a nonlinear system, but we see the form of the linearized system, which correspond here to the left-hand side. So the linear model is written here, in which we have replaced the the right-hand side here in the equation by some quantity which are assumed to be known. Okay, so what we see here, we see that this coupled system is actually, when we take the linearized form, it's a triangular system. It means that we can solve first the system for Q, and next solve the corresponding equation for A. So this is the triangular form of the previous one, in which we have used some lifting for the non-homogeneous boundary conditions. So the first step to study the system is to obtain good estimate for the linear model. So we look for solution for A in H1 with values in H1, and for the flow rate here Q in H1, L2, L2, H2. And this is for each component here of the network. So in each vessel. So I introduce here the corresponding norm. And what we obtain an estimate for the non-homogeneous linearized model in this form. And this is crucial to study the existence of solution for the nonlinear model. So in the result we have obtained with Debayan and Arnab, we have introduced the notion of maximal strong solution. So what is a maximal strong solution? It's a solution to the system in any time interval 0 capital T, which is strictly less than some Tm, the maximal time of existence. So we have to characterize this maximal time. And so either Tm is infinite or it is finite. So when Tm is finite, the solution exists up to Tm, but explode at Tm. And the explosion criterion is given here. So it means that when T tends to Tm, either this norm explode or the cross-section here goes to 0. And the result we have obtained is the following one. So for some regularity property for the initial data and some compatibility condition between the Dirichlet condition here for Q and the initial condition, we obtain the existence of a unique maximal strong solution. So I would like to insist on the fact that both the solution and the maximal time are unique. So this is the result we have obtained. Some idea about the proof. So it is based on the estimate I have introduced before. So first we introduce, we prove the local in-time existence of solution by a fixed point method. So for the fixed point, we have to introduce some ball. And so the ball depends on two quantity. So first we have to look for a solution which satisfies some bound here and for which the cross-section is far away from 0. So these two parameters, mu and gamma, has to be chosen. So mu large enough and gamma small enough, and mu and gamma depends on the initial condition and also on the non-homogeneous boundary condition. Choosing correctly mu and gamma, we prove the existence of a local in time solution by a fixed point method. And after that, we extend any local solution to a maximal one. Of course, the difficult point is to prove that there is some explosion. We prove it by contradiction, and we next prove the uniqueness of solution. Okay, so what I present here is the existence result in the case of Dirichlet condition on Q. But we can also choose some other boundary condition. For example, we can introduce boundary condition on the velocity, even for the system described by AQ. So it corresponds to this type of boundary condition, and it's actually a nonlinear Dirichlet boundary condition for Q1. We can also introduce boundary condition on the pressure. In that case, using the pressure law, this boundary condition for pressure correspond to a nonlinear boundary condition of Robin type here. So we just use the fact that dA over dt is equal to minus dq over dx to obtain this Robin boundary condition. Okay, I introduce also another type of boundary condition that I call penalized Robin boundary condition. Why? Because we take some parameter epsilon and we take here some nonlinear term. So when epsilon goes to 0, this Robin boundary condition gives an approximation of the exact Dirichlet boundary condition Q1 equal to H1. And we do the same for the vessel 2 and vessel 3. So I introduce this type of special boundary condition because we prove some stability estimate in that case. So the existence of solution we have obtained before for Dirichlet boundary condition can be extended to this type of boundary condition. So either on the velocity, the pressure of this type of penalized Robin boundary condition. So I would like to end this part by introducing the energy identity. So we have introduced this energy here. So even if we have a cube here, for which there is no sign, due to the presence of V2 of a term, we can prove that it is actually an energy. So it is a non-negative quantity. And the result we have obtained is the fact that for any maximal solution, we have of course, independently of the boundary condition, we have this kind of energy identity. But we find here the boundary condition in some sense, since if Q1, Q2, and Q3 are prescribed, we obtain something here. But there is no sign on that quantity. It's why in the case of penalized Robin boundary condition, it's interesting to prove this stability estimate here, for which now we have positive quantity on the left-hand side and the corresponding data on the right-hand side here. Of course, this quantity is not uniform with respect to epsilon, since when epsilon tends to infinity, these two quantities becomes infinite, but it's uniform with respect to viscosity here, nu I. And so when nu I tends to 0, which corresponds to the case of an hyperbolic equation, this quantity, this stability estimate is still valid. So it is still valid for C1 solution of the hyperbolic corresponding hyperbolic system. So I end the talk now by proving some extension for the AU model and also to general network. So let us start with the AU system. So I have written here just one equation for AU, but we may have this type of equation in each vessel here. So the new point here, interesting point, is that we have no maximal regularity for U. We are not able to prove that. We have only maximal regularity for AU. And this is why the class of solution we obtain is not a classical one. Why? Because it is not a vector space. Of course, this corresponds to vector space, the same for U. But we have to introduce also the fact that the product AU, which corresponds to Q, belongs to this space. And because we take care of the product, we have not a vector space, but we have a metric space. And so we can introduce the distance between two family of solutions satisfying this, this regularity property. And so I denote by dt of the distance when I take this norm over the interval 0t. So introducing this distance, we can define the notion of maximal strong solution for AU, and the explosion criterion here is given in terms of this distance to the 0 solution. So introducing this criterion, we obtain exactly as before, as for the AQ system, this type of existence of maximal strong solution for the AU system under the assumption that there are some compatibility conditions for the initial data. And the proof of this is based on the fact that we prove the equivalence between the AQ and AU system, at least for the class of function having the regularity that we have identified for AQ and AU. Okay, now the last part corresponds to the extension to a general network. So I have taken here a special network, but it can be any arbitrary network. So what we need an oriented network, means we need something which is, of course, connected with several segments. So on each segment, we have to choose an orientation, which can be arbitrary. We have to identify the junction point here, and we have to identify the inflow and outflow conditions. So for example, here, this corresponds to an outflow condition, and this one here corresponds to an inflow condition due to the orientation. But if I take here an inflow with a negative value, it's exactly equivalent to an outflow with a positive value. So it's why the orientation is needed to write the set of equations, but it's not really important. So this corresponds to what is called the circle of Willis, which is a part of the network we find in the brain. And so for this type of general network, we can obtain exactly the same existence theorem as before. Of course, we have to write properly the corresponding conservation law of flow rate and equality of pressure at the junction point. If we do that, and if the initial data and the boundary condition satisfy some compatibility condition at this junction point, we obtain exactly the same type of existence of solution as previously. And we can also change the boundary condition exactly as before. So now I am on time and I can conclude. So what we obtain the existence of a maximal strong solution for a 1D model in a complex network. We think that this can be very helpful to obtain, even if it is a simplified model, to obtain a complete model taking into account the cerebrospinal fluid flow and also the autoregulation phenomenon. We think that it may be helpful for designing estimation algorithm for the pressure and for parameter, and also to analyze uncertainties of this model. And I give here the reference of the two papers with Debayan and Arnab. This corresponds to the 3D model and this one to the 1D model. And I thank you very much for your attention.
So thank you very much, Professor Raymond, for such wonderful talk. So now I request participants. So if you have any question, please write in the question answer box. So already we have few questions, but you can write down your questions in the question answer box. So Professor Raymond, so we have some questions from the participants. So I am conveying you on their behalf. So there is a question is that is writing, hi, my name is Amar, very intriguing and informative presentation. I am curious to know on slide 18, what type of shell theory has been used?
Okay, 18. So 18 here or?
Slide 18, what type of shell theory has been used?
Okay, so here, so the equation for the shell is written here. Okay, why it is this? Because we make some asymptotic analysis for the shell. So the full model is here. We start with a Coiter shell model with viscoelastic term. So the viscoelastic term are this one, no, so and this one too. So there are three viscoelastic terms. And we try to see what are the dominant coefficients here. So what we observe is that this coefficient here is of order h over r squared, which is not necessarily small because h over r is small, r is also small, and so finally this quantity is not necessarily small. It depends, of course, of this coefficient. So we can neglect this term. We can also neglect this term, but these two coefficients are of order h over r squared. If we look to the other coefficient, for example, this one, since h over r is small, when we take H2 over R2, it is even smaller. And we multiply by H, which is also small. So this coefficient here is very, very small. And the same for the other coefficient. So in this asymptotic analysis, the only important coefficient are these two. The other can be neglected. So if we take these two coefficients here, the equation reduces to that one. So now I would like to express this equation in terms of A and Q. And so due to this relationship here, and if I introduce also the area of reference configuration for the cross section, I see that eta, which is here, is just given by this. And so now, when I put this into this equation, I obtain this quantity here times some coefficient. And when I take the time derivative of this quantity here, so this is independent of time. So I take d over dt of this quantity divided by 1 over 2a. And so, this is given here. So maybe, sorry, I think the A is missing here. Yeah, I don't know. Okay, sorry, I'm not sure. Of course, I have taken here the reference configuration, but it corresponds to some linearization. So maybe the A is missing. So in any case, this equation here is taken from this relation and this identity. And so the shell equation we have here is only the asymptotic approximation of this Coiter shell model. Is it clear or not?
Okay, so I think it's clear because he has written down. So
okay.
Explanation. So there is another question: why the asymptotic expansion is truncated at epsilon to the power 1? What would be if we consider only the leading order term epsilon to the power 0?
Okay, so if we take, okay, it can be done. So when I say that we obtain an equation for V and Q, so it's not obtained directly. We first obtain an equation for V naught and Q naught. I do not remember, but it's a too simple model. And so more sophisticated, because when we take just the first quantity, we lose the information about the geometry. And so in some sense, we obtain a very poor model. Of course, the model can be written, but it's too poor to describe the evolution of the shell.
Okay. So if anybody else has some questions, please raise your hand or ask the questions. After that, I will ask 2 questions.
So I have one question.
Yeah.
Yeah. So you have shown after the nonlinear models, you showed the linear models.
Yeah.
My question is that, is there any, I mean, null controllability result known for this system?
Okay, so no, there are some, okay, what is difficult here?
Yeah.
So some controllability result can be obtained for the linearized model, but even for the linearized model, we have no controllability result. Okay, I can share some other slide if you want. I can explain this. Yeah, it's okay.
Yeah, it's sure.
Okay, I have to go to some of the talk. I do not remember. Maybe, sorry. Okay, that one and that one. Okay, I can go to the end of the talk. Yeah, about control and estimation, and I can put it in full screen. Okay, so I've written here the previous model, but the linearized one. And so the linear model can be written like that. So linearize around either the initial condition or the reference configuration. And so I have listed here the results which are known for this linear system. So it depends on the coefficient alpha, beta, gamma, and delta. So in the case when alpha and delta are 0, so alpha and delta are 0, in 2012 with Shirshendu and Maithili Ramaswamy, we have proved that the system is stabilizable, but not controllable, I think. If the control acts everywhere in the equation. So we cannot take localized control, and there is no stabilizability for localized control. So either by F or by Dirichlet condition. So there is a conjecture saying that, okay, the linearized system is stabilizable by a control acting everywhere. So we do not know if it is true or not. The case of a network that I'm going to consider here is fully open, even in that case. And the null controllability, we cannot speak of exact controllability because we have a parabolic equation. So null controllability is not known. There is some result by Shirshendu, Debayan, Maithili, and Debanjana, I think. Published in Journal of Differential Equation, but for periodic boundary conditions. So these are more or less the results which are known. So even for the linearized model, even in a single vessel, everything is quite open. And I think there is no result in the case of a network, even in the case of a simple bifurcation. So of course there are many, but I know that Shirshendu work on that, and maybe has some other result, but I think there is it's quite difficult to Yeah, it's quite difficult to say something for the nonlinear model.
Thank you.
So there are two more questions here already.
Mhm.
One is, thank Jens Osborne, thank you for your talk. Which numerical methods would be appropriate for approximating solution to the system? Would they differ
Okay.
between AQ and AU models?
Yeah. Okay, so it's a very interesting question. So let us go to the system written. No, sorry. Yeah, the system written like that. Okay, so for this system, there are two types of method. The first one is to use some implicit or semi-implicit scheme for the hyperbolic part, and to treat the viscous term in a fully explicit manner. So this is one possibility. There are a lot of papers in the literature on that. The other way is to use a splitting method, saying that we first solve the elliptic equation and make some correction with some parabolic part. So it's a splitting method, also well studied in the literature. We made some attempt to use some compact scheme to solve directly this system. This is under investigation, but not yet obtained. So there are a lot of ideas, and in the case when nu equal to 0, so people use mainly numerical scheme, finite difference scheme for hyperbolic system. And since even if we look at the hyperbolic part, nu is small, the behavior of the system remains mainly of hyperbolic type. It's why we must be very careful in the numerical scheme for solving this type of system.
So there is another question. Sorry, I am from non-mathematics background. Can you explain the Navier-Stokes equation, its importance? Maybe he's asking that where it arises or what it models.
Okay, so I can go to Navier-Stokes. So, okay, so Navier-Stokes is a model for describing fluid flow in the case of viscous flow, incompressible, and Newtonian flow. So, okay, it's a set of equations which is nice and which gives some complexity, but there are some more sophisticated models for describing blood flow, especially people study non-Newtonian flow. So in that case, we have even a much more complicated equation. So I should say that in the case of incompressible flow, so this is the incompressibility condition. This is one of the, in the case of viscous flow, one of the most simple we can assume that the density varies. In that case, we have to write the density-dependent Navier-Stokes equation. So we have to modify here the conservation of mass. And so in some sense, it's a model which is quite complex, but not so much. And there are other models which are more complex than that.
Okay, thank you, Professor Raymond. So I have the two questions. First of all, that since Prashanjit asked that one, so you show that this is corresponding to the ODE and the parabolic equations coupling somewhere. So is it something when you start the model with a suppose viscosity is 0, so some kind of hyperbolic model and the coupling in the boundary, some controlability results are known when in this kind of things?
Yeah, so I see what you, okay. So in the case when nu is 0, yeah, it's given here. So we have a quasi-linear hyperbolic system. Of course, you can look at the model in a simple vessel. I do not know if there are results for that model. What I know is that there are a lot of results for hyperbolic system by the school around Ancona, Coquelit, and Marsden, and also yeah, some other guy in this school have studied the controllability of such model. So I can give you a reference on that, but I do not know exact if for this exact model there is or not controllability result.
So now the questions comes. This is in this system for the controllability issue. The difficulty is on the boundary, the junction, whatever the conditions you put. This creates a difficulty to study this kind of nature controllability for this one. The coupling in the boundary.
Not necessarily. Yeah, so the first, okay, before considering a system in a network, you have to say something about a single vessel. Mm-hmm. So if for a single vessel, you have some controllability or stabilizability result, mm-hmm. You can expect to extend this type of results to a network like, for example, just bifurcation. So it should be nice to do that, but you cannot expect to have something for bifurcation if you do not have the corresponding result for a single vessel.
Okay.
So you have to clarify what you can do for the simple model and try to extend to a more complex model after. But I think that, for example, assume that you obtain some controllability result if you control by Dirichlet condition at the two extremities of a vessel. It should be natural to show that if you have a bifurcation and if you control at the inflow condition and at the two outflow boundary condition, you can have the same controllability result as you obtain for a single vessel. I think it can be done.
Okay. And another question is that you show some time Tm, right? So the maximal time. So there exists some maximal time, and it can.
Yeah.
It can be finite. It can be infinity.
Yeah.
So the point is, it can in this case, if you can choose some kind of a control to prevent with a finite case, you can prevent this blow up?
Yeah. Yeah, it's a nice question. Of course, you can, yeah, it's given here, yeah. So, of course, you can use some device in order to prevent some explosion. And it's actually what is done, for example, in the brain, because the auto-regulation phenomenon is a feedback which prevent the fact that the radius of the vessel goes to 0. So there are already a feedback mechanism in the brain in order to maintain a good regime for the blood flow. Yeah, and a nice result is to say, okay, there are some models for the autoregulation phenomenon, and it should be nice to have a mathematical model and to say, yes, the model derived in biology are good and we can prove some stabilizability result. It should be really interesting to do that.
Okay. So thank you so much, Professor Raymond, for making this session successful. We hope to get your participation. So participation in future talks as well. Prosenjit, it's over to you now. Prosenjit, mic is off. Prosenjit, your mic is off.
So for the participants, we hope that you have thoroughly enjoyed Professor Raymond's talk. We'll meet you all in 2 days from now for Professor Jean-Michel Coron's talk on stabilization in finite time of some partial differential equations. Thank you. Bye-bye. And I'll request everyone to leave the platform now. Thank you all. Thank you, Professor Raymond. Thank you, Professor Raymond.
Thank you.
Thank you.
So I'm ending the meeting.
Okay, Prashant. Okay.
Bye.
Bye.